Okay, let's talk now about complex numbers. And what is a complex number? Well, we looked at the number system, didn't we? A couple of lessons ago, and we said, right, well, all numbers are either down here as real numbers, or as complex, or imaginary, unreal numbers, and then within the real there's rational and irrational. These have all got little symbols, not irrational. Real is like there's complex, has that symbol there. Okay, now the complex numbers arise from trying to solve equations of this nature, where the real numbers don't do it, do they? Square any real number and you've got a positive. So what squares to -1? Okay, well, let's make up an answer to that. Let's make up that that I squared. If we say that, if we make up if we make up this concept of I, and I squared is equal to -1, then we can say from here that x is equal to I, right? Because that's what we got here. So an I is equal to the square root of -1. Now we've got something to work with, right? So we're making up this number and saying, well, there is something that squares to -1. It's I. We're going to go with that. And so when we're presented with this sort of problem, then we just deal with it as a complex number. Okay, so complex number, that's where it stems from, and they have the form complex numbers have the form Z. So this is the sort of standard notation here for complex numbers. Z is used, and I'll just put a little stroke through there. So it's not a 2, it's a Z. A plus IB, where this A bit of it is the real part of Z. That's the real part of Z, and the B part is the imaginary part of Z. Where A and B are both real numbers. A, B are an element of the real numbers. Okay, so we set it up like so, and we say, all right, well, what's this concept of the Argand diagram? Well, that's trying to therefore look at graphing complex numbers. So complex numbers can be represented on the complex plane, have the form, and can be represented on the complex plane. We're used to the XY, the real plane, the Cartesian plane. They're represented on the complex plane known as the Argand diagram. Now it's also known as the Gaussian plane, but I'm going to refer to it as the Argand diagram, known as an Argand diagram. I'll just pause there. Now the Argand diagram has not an X and Y axis, or not XY axes, but an imaginary axis and a real axis. Okay, so we just put arrows on the end of this, so it looks exactly the same, it's all set up the same, but here we've got on the horizontal, we've got our real axis, and on the vertical we've got the imaginary axis. Okay, so for example, let's plot 4 minus 2i on the Argand diagram. Right, the Argand diagram, remember, is just running out of room there. 4 minus 2i is the complex plane. So 4 is the real part. So we go across 1, 2, 3, 4. And minus 2 here is the imaginary part. So we go down 2 on the imaginary axis. We end up just here, don't we? And that, all right, we've just gone down 2 to there. So this is 4 minus 2i. That's the point, 4 minus 2i, on the Argand diagram. Okay, so we're getting through some things here. That's nice. The next little thing we want to look at is what's called the modulus of X. Now the modulus, if you remember, the absolute value of a number is its distance on the number line from the origin. So the same idea here. So if we go back to the modulus of, say, 3 is equal to 3. The modulus of minus 3 is also equal to 3, because both 3 and minus 3 are the same distance from 0 on the number line. Okay, we talked about this, didn't we? And this absolute value of 3, or the modulus of 3 and minus 3, are the same because of this distance here, and it's defined as the distance to the origin. Similarly, with this now, if we've got z equals 4 minus 2i, then we're looking what that, if z is equal to this point here, this complex number 4 minus 2i, if that's the case, then the modulus of z is the distance of that point from the origin of the complex plane. So it's that distance there. And we know enough at this stage of our lives to realize that that's a Pythagoras problem, and so the square root of the modulus of z would be equal to the square root of 4 squared plus 2 squared, which is 16, and 4 is the square root of 20, which we like to write as 2 square root 5. So that's the modulus of z. But generally, the modulus of z will equal the square root of a squared plus b squared when z is written as the complex number a plus bi. Okay, just one other thing I want to cover really in this screencast is the operations on the complex numbers. So adding, subtracting, and multiplying, and it's really just an intuitive thing. So I'll just let me take a note. I'll pause, and so there's some notes to take when I unpause. Okay, so just some notes for you. Operations on the complex numbers. By operations we mean addition, subtraction, multiplication, and division. Eventually, we're just going to look at the addition, subtraction, and multiplication initially. So z1 plus z2. Let's have a look at what results here. Well, it's just the sum of, so 3 minus 5i. The great thing about complex numbers is pretty logical and intuitive. It's not going to challenge your thinking too much in terms of what you've been used to. 3 minus 5i plus minus 1 plus I. If we look at it as there's our sum of z1 plus z2, we add our real components. 3 minus 1 is 2. We add our imaginary components. Minus 5 plus 1 is minus 4. So 2 minus 4i we get. For b, it's z2 minus z1. So we say z2 is minus 1 plus I, and we subtract z1, which is 3 minus 5i. So we get minus 1 minus 3, which is minus 4, and we get I minus 5i, which is plus 6i. Minus 4 plus 6i. So it's a perfectly intuitive process. Now the multiplication, the product of the two, is just what you'd expect if you were just to do a binomial product. So z1, z2 is 3 minus 5i for z1 times z2, which is minus 1 plus I. If we multiply those together and use our FOIL approach, it's the same. So 3 times minus 1, 3 times I, minus 5i times minus 1, and minus 5i times I. Now this is minus 5i squared, which I'll write down, I squared, but you'll know minus 3, I'll put these two together, plus 8i. This I squared is minus 1, isn't it? Right, that underpins everything we do. I squared is minus 1. So this value here is minus 1. So minus 5 times minus 1 is plus 5. And so we end up with minus 3 plus 5, which is 2 plus 8i. And we've done our multiplication. Okay, so that leaves us to do exercises 3D and exercise 3E, and I'll make another YouTube lesson for the following complex number exercises. So I'll leave it there for now.